I'd like to welcome today's defense. For the gentleman here, that will be presenting his work, design and analysis of dynamic configuration networks. So just before we proceed with the presentation, I'd just like to introduce the members of the jury. So there's myself, which is the president today. So I'm Jonathan Rodriguez from the
Cristina López,
I'm Matías Toril from the University of Navarra.
Thanks. So the layout for today's exam. So we expect you to present for around 50 minutes or so, and then after this, the jury members will take the opportunity to ask some questions. Okay, so when you're ready, let's start.
Good morning, everyone. Thank you all for being here today. I am pleased to present today my thesis titled Design and Analysis of Dynamic Reconfiguration Mechanisms for Next Generation Mobile Networks, which proposes and evaluates mechanisms to adapt mobile networks to achieve better performance. This presentation is structured as follows. To begin, I will provide an overview of the context and scope of this work, and then I will present in detail the contributions in this thesis, highlighting the key findings and innovations of my research. Finally, I will conclude this presentation by summarizing the results of this work. Mobile operators are expected to encounter significant challenges in the near future. The number of subscriptions is steadily increasing, with smart devices replacing legacy mobile phones that lack data service capabilities. In addition, an increasing number of machinery devices are being connected through mobile networks to benefit from key characteristics such as ubiquity. Combining both factors, mobile networks will need to handle an exponential increase in the data traffic they must forward. And this is occurring in a context in which users are increasingly demanding lower prices for their data services, and there is a strong competition in the sector to meet these expectations. On the other hand, use cases are emerging that require wireless connectivity, and both mobile operators and standardization bodies are promoting 5G and beyond technologies as the enablers for these applications. Examples of such use cases include remote operation in surgeries and other health procedures, collaborative working, autonomous vehicles and road safety, agriculture and farming, and entertainment. These examples just represent a subset of the complex emerging use cases that mobile networks will serve in the near future, and are characterized by having strict network requirements in terms of throughput, latency, reliability, and other metrics. This is illustrated in this diagram, which shows how, depending on the use case, the quality of experience is highly dependent on certain metrics, but less dependent on others. As I said, complex emerging use cases have stringent requirements for one or more of these KPIs. Today, it's not feasible to offer a general mobile data service maximizing all these KPIs to all the services and users, at least in a cost-effective basis. And therefore, 5G networks need to reconfigure themselves dynamically to guarantee compliance with service level agreements. Several paradigms and technologies, some of them are listed here, have been proposed and standardized to facilitate these reconfigurations. But due to their novelty and the scarcity of experimental equipment, there are currently limited studies analyzing how effectively these technologies can help to meet the requirements of emerging use cases. The main objective of this thesis is to fill this gap and contribute to the state-of-the-art of in mobile network technologies by proposing and analyzing mechanisms that enable 5G and future networks to dynamically adapt their resources in order to support use cases with stringent requirements effectively. The contributions of this thesis are classified in 6 works, And as shown in this table, each of them contribute to the state-of-the-art of the reconfiguration of radio access network or core network resources, the evaluation of KPIs, or the analysis of emerging complex use cases. Okay. My first contribution provides a framework to relocate the equipment in a radio infrastructure composed of SDR devices to different operators, for example, according to agreements or dynamic network conditions. Operators have traditionally shared infrastructure and to manage more base stations at reduced cost. And this trend has ended with infrastructure providers owning masts and other assets and leasing them to many operators through outsourcing. This allocation is today static and cannot be adapted to the dynamic behavior of the end users. And this work defines a framework that enables infrastructure providers to allocate the radios to the tenant operators based, for example, in the location of the end users and their loads. In the example shown here, a new service in gray has emerged at a certain moment, whereas the users have also moved to different locations. And after this new setting, the infrastructure provider has determined that there is a new optimal radio allocation strategy and relocated this for SDRs to different operators. The architecture of the solution is shown in this picture here. Instead of directly allocating to the SDR the baseband function, what we do is we introduce a new entity, we call it the transceiver coordinator, and each of the SDRs in the infrastructure is allocated with one instance of this function, which configures the SDR with the corresponding sampling rate, bandwidth, and central frequency, while at the same time acts as a relay between the corresponding baseband function and the SDR. This setup allows for the baseband function to be replaced on the fly by simply switching the communication on the transceiver coordinator to the corresponding baseband function, and also by keeping the radio connected, we can reduce the initialization time, and also we can avoid to reconfigure those parameters that are already configured in the radio that match the values expected by the new service. We implemented this solution in a real testbed, as shown in this video, where in this personal computer we run both the transceiver coordinator and 4 LTE baseband functions, and we commanded the transceiver coordinator to switch from one baseband function to another each 1 second sequentially, configuring the central frequency in the SDR. During radio reallocation, the baseband functions cannot make use of the SDR until the reconfiguration is complete. And this means that each relocation entails a downtime. Therefore, the number of relocations the infrastructure provider can perform is constrained by the target availability of the own infrastructure. We analyzed the different steps that must be performed to configure the SDR and measure the time required to perform them using the commercial SDR we show in the video. And the results are shown in this table. By preloading the entire network stack before radio relocation and then waiting for the infrastructure provider to allocate the radio to the service, we can reduce the downtime to just 126 milliseconds. But however, we can further reduce this downtime by avoiding to reconfigure those parameters, as I said, that match those requested by the new service. And also, we can implement a signal processing function in the own transceiver coordinator to adapt the digital signals for the transmission and reception signals by software in order not to reconfigure some of these parameters. In the sample shown before, we had 4 channels of 5 MHz each, so we could configure the SDR to operate at 20 MHz and then channelize and resample by software the transmission and reception signals. This is much more computationally expensive than configuring the SDR with the appropriate bandwidth and central frequency, but by reducing the downtime, we also increase the dynamism of the infrastructure. In summary, in this work, we have proposed a framework that enables infrastructure providers to relocate the SDR to different radio services, which allows the adaptation of the infrastructure for better overall performance. This solution enables new business opportunities, such as out-tuning the radio devices, that is, let the operators bid for the use of a specific radio equipment. And well, we built an experimental testbed and evaluated the downtimes resulting for the different radio configurations that are required to configure the SDR when switching from baseband functions. Our experiments demonstrated the validity of our proposal and showed that it is possible to frequently relocate the radio to different operators without significantly impacting the infrastructure availability. In my second work is focused on coordinating the transmissions of mobile and wireless LAN technologies in unlicensed bands to better control QoS in these scenarios. LTE introduced operation in unlicensed bands to extend the capacities of mobile networks or for a standalone operation similar to Wi-Fi. And this was also continued in 5G standards. In unlicensed bands, mobile networks coexist with other services, especially with Wi-Fi. There exist scenarios like malls, but more especially enterprise facilities, in which an operator may be granted to deploy both technologies in unlicensed bands with exclusive access. And in this case, the operator may be interested in allocating the channel resources according to a strategy, which may be based on loads or network requirements. But unlike mobile networks, Wi-Fi devices, at least legacy Wi-Fi devices, can transmit as soon as they consider the channel even. This work aims to define a solution that allows an operator coordinating the transmission of these two technologies, and by coordinating the transmission, this solution allows the operator to decide how the resources can be allocated to one technology or the other, but also reduces the collision between transmissions of different technologies, which, how to explain, when devices from different technologies use their own MAC processors, when they coexist directly in the same frequencies and space, this can result in devices not detecting transmission, detecting the channel as either when there is a transmission that can be received by other devices in the environment. And this is an issue that has been reported extensively in the literature. We studied the standards and identified two mechanisms that allow to command Wi-Fi and devices to share the channel with the mobile network. These mechanisms allow to define how the resources of the channel are allocated to each technology and work with the system and devices without requiring any modification in the end devices. On the one hand, CTS to self is a mechanism that is used to inform every device and every Wi-Fi devices about an upcoming transmission and its duration. And it can be used to make Wi-Fi devices to defer in a predefined time, and then we can use the wall channel to perform mobile transmissions. That is, with this mechanism, we can multiplex in time, in the time domain, Wi-Fi and mobile transmissions with both technologies exploiting the wall bandwidth of the channel. On the other hand, TSA is used by access points to move end devices to different frequencies in case the access point detects a priority service such as satellite operating in the same frequencies. But we can use this mechanism to just alter the bandwidth of the channel so that we make room for new services in the frequencies we left vacant. As a result, both the mobile and the Wi-Fi networks can operate simultaneously, but within the allocated frequencies. To analyze these proposals, we developed an analytical model to estimate the network capacity of Wi-Fi 5 and LTE-LAA when the technologies coexist in a licensed bands, directly or well, when they coexist directly, that is using their own MAC processors in the same space and time. And we also extended this model to estimate the network capacity when using our own the solutions we proposed. The difference between the baseband model and those in the literature is that our baseline model considers LTE traffic classes, but more especially MPLU aggregation, which is a key feature of Wi-Fi that enhances a lot data rates. This table shows the performance of Wi-Fi and LTE LAA networks when using our solution for different bandwidths and resource shares. This column here shows which is the sharing approach of those we propose that yields better performance in terms of aggregated network capacity, that is the sum of the network capacity of Wi-Fi and the network capacity of LTE. And here we show the capacity of Wi-Fi and LTE LAA for traffic classes 1 and 4, and the sum of these two results. And in this column, we compare the aggregated network capacity with that capacity we would obtain if the networks coexist directly. And as shown in this table, our approaches not only allow us to configure how the resources are allocated to one or the other technology, but also outperform in most cases direct coexistence. And in addition to this analytical evaluation, we developed a simulator using the well-known tool NS3. And we implemented both solutions and measured the throughput and the saturation to estimate the network capacity. And the results we obtained matched those we get using the analytical model, validating our model, and we also demonstrated the feasibility of our solutions. So the proposed mechanism shown to be able to allocate the resources of the channel according to the ratios defined by the operator and also provide better performance than direct coexistence. It is also worth to mentioning that our analytical model does not take into account that devices may decode signals below the threshold at which they detect the channel as idle, as I mentioned at the beginning of this chapter. As this mainly, we haven't done that because this mainly depends on how the devices are positioning on the environment and other environmental conditions such as propagation. And this effect may lead to undetected collisions in environments where devices using different technologies are spread, reducing the performance. But when using our solutions as we multiplex transmissions from different technologies in time or frequency domains, these results are not affected. Therefore, the difference in performance when using our approaches compared to direct coexistence are actually greater. However, they have two major weaknesses. On the one hand, they are only suitable for specific scenarios in which the operator is granted with exclusive access to use the channel, especially the solution that relies on CTS. However, this is not unrealistic as it may appear, as even the 3GPP has defined different channel access procedures for unlicensed operation in 5G networks, whether the operator has exclusive access to the channel or not. And on the other hand, the performance could be affected if the CTS or CSA frames are lost, but in any case, this is unlikely to result in a substantial decrease in performance. So in summary, this work presented two mechanisms that allow mobile operators to manage how the resources are allocated in unlicensed channels between mobile and Wi-Fi networks. And in addition to achieve this primary goal, the solutions also outperform direct coexistence in terms of network capacity. We developed an analytical model to evaluate the performance of Wi-Fi and LTE LAA under direct coexistence, including NPU aggregation, and complemented this model to evaluate our proposals. We then evaluated with these models the performance of the two networks when using the sharing mechanism and compared them with direct coexistence. And finally, we developed a simulator with which we validate the accuracy of our model and the feasibility of the solutions. Okay, moving to my third work, it seeks to contribute to the state of the art of solutions for assessing compliance with KPIs for emerging use cases. Emerging use cases have stringent and diverse network requirements, and 5G networks must meet dynamically, must readapt themselves dynamically to meet them. Applications will demand increasingly lower delays, and networks must ensure that these requests are met by implementing tools to measure these KPIs. And in this regard, mobile networks have particular characteristics that make it difficult to measure the delay in one of the paths, uplink or downlink, when we do it separately. The typical approach of measuring the routing tag and dividing this value by 2, therefore, is not applicable to these networks. We proposed a simple framework to evaluate the delay in the communication between any two nodes in a mobile network in just one of the paths, uplink or downlink. The delay in this framework is measured as follows. The source and sink nodes are first synchronized using a protocol like PTP, for example, and this may require an additional interface because mobile networks may introduce higher jitter, and this may make the device not to maintain synchronization. But once synchronized, we transmit synthetic traffic following the specific pattern we want to test, and we log the timestamps at which devices transmit and receive the data. Finally, we compare both results, and with this we determine the delay. These pictures here are an example of the result we got with this framework. The picture up the left shows the delay in the communications for different loads in different network slices with different priorities, whereas the other two measure the delay, the evolution of the delay in the time domain under regular conditions or saturation. And summing up, in this work we presented a framework for measuring the delay in either uplink or downlink between any two nodes in a mobile network. We implemented this solution in a testbed and measured the delay of our 5G standalone network under different loads across multiple network slices. My next work addresses a critical challenge for the future of mobile networks, which is securing these networks against attacks under the exponential growth of connected devices, especially machinery devices. This is crucial. This is a crucial issue for several reasons. First, aside from the exponential growth of connected machine-to-machine devices, most of these devices are extremely simple and cannot implement complex security functions. And in addition, among the emerging use cases, there exist applications that require high reliability, such as security systems, energy plants, factories, airports, etc. And attacks may lead to significant costs. We have recently lived such a situation with a massive failure of computing equipment running Windows last week. Many solutions already exist to prevent denial of service and other attacks, but the complexity of these solutions, these legacy solutions, increase not only with the traffic load, but also with the number of devices being analyzed, because this would require to maintain more contest sessions. Additionally, effectiveness of this solution often depends on the volume of malicious traffic being sent for each of the devices in the network, but in high-density networks, it is easier to distribute the load among a high number of devices and therefore make the attack less obvious. In this work, we defined a lightweight solution to detect denial of service attacks in massive IoT networks. And this solution leverages one of the most recognized characteristics of these devices, which is that IoT communications follow very predictable patterns in terms of payload size and consistent intervals. The idea is to use traditional traffic inspection tools, solutions, but reduce the number of data flows that are being analyzed with these solutions. To do this, an SDN application will monitor the volume of traffic of the data flows and compare this value with the expected value. Data flows that present suspicious behavior, that is those that differ from the expected load, are redirected to an isolated network slice and analyzed with a regular inspection function. This ensures that suspicious traffic is still processed until malicious traffic is detected and blocked. Because within this suspicious traffic, there may exist legit data flows. For example, the traffic may deviate just because there is an update or a strange event on these devices. And by splitting the traffic into two isolated network slices, we also protect the traffic of these devices that do not show deviations on their behavior. Once the traffic is moved to this quarantine slice, it is analyzed by a legacy inspection tool, and malicious traffic is blocked, and the regular traffic is returned back to the original slice. By introducing this two-step process, we reduce the number of data flows that are analyzed by the legacy inspection function, which reduces the computing capacity required by the operator to protect the network. We developed an analytical model to estimate the number of malicious and regular data flows related to the quarantine slice, based on metrics such as the quantity of malicious of infected, let's say, devices in the network, and the amount of traffic, of additional traffic sent by these devices, or the threshold we use to determine whether a set of data flows is suspicious or not. We use the information from the literature regarding real traffic behavior, including payload size and transmission frequency, for 4 classes of end-to-end devices that are typically used in industry. And these two graphs are just an example of the results we obtained. They show the amount of data flows that are sent to the quarantine slice as a function of the amount of malicious data flows. As shown under any configuration, well, most malicious data flows are sent to the quarantine slice. It is worth to mention that the evaluations we conducted, they consider that data flows are assigned to SDN flows following uniform distribution, and as a result, they contain mixed traffic classes and it's less predictable. But by considering the traffic class of the data flows when creating these clusters, these SDN flows, traffic patterns would be much more predictable, and therefore it would be straightforward to detect deviations in caused by malicious transmissions, for example. And that is, the solutions should be able to detect all SDN flows containing malicious traffic or showing deviations in their traffic patterns. In addition to the theoretical analysis, we implemented this solution in a testbed in order to measure the delay in steering the data flow to the quarantine slice in a real-world setup. And for this, we deployed a TestLT base station and core network and an SDN controller and bridge. Steering the traffic to the quarantine slice requires to deploy the quarantine slice, which in LTE involves to deploy an SPGW, and in 5G would be an UPF, and migrate the context information of the corresponding data sessions to the new node, and then set the appropriate routes between the base station and the core network to forward the traffic to the original slice or to the quarantine slice. These stages took almost 1 second in the first phase and 34 milliseconds and 4 milliseconds in the other two. But note that this does not mean that the traffic is delayed during this time. When we consider that the traffic should be inspected in the quarantine slice. What it means is that the traffic is still processed through the original slice until all these 4 steps are performed. And in this regard, the delay can be reduced to just 4 milliseconds if the operator maintains the quarantine slice running and mirrors the context information of all the data sessions beforehand. Although this would imply a greater use of computing resources. In summary, this work presents a solution to reduce the complexity of DDoS prevention systems in massive IoT networks by performing a lightweight analysis of traffic patterns. It keeps the set of devices showing regular behavior isolated from those that show deviations, ensuring that the performance of the former are not compromised. And we have developed a model to quantify the number of malicious devices quarantined using based on different metrics, and implementing this solution in an experimental testbed to measure the time required to redirect a suspicious data flow for in-depth analysis. My fifth work deals with edge computing, which is has very significant hype surrounding this technology. As services are deployed closer to the end users, this paradigm should naturally provide lower delays. However, to what extent can edge computing improve the performance to enable emerging services with stringent constraints? How does it compare to cloud computing and onboard computing? These are the questions we seek to answer in this work. To this end, we developed an application for remote controlling a drone. The application uses deep learning to recognize and track a person using a camera embedded on the drone, and uses the position of the person in the frame to determine how the drone should move. In this test, we recorded the image that was captured by the drone, and here we print the information generated by the drone about the position and how the user is being tracked by the drone. In offloading, we split the application in 2 parts. Basically, we started the complex parts, those related to the detection of the person, and we ran them in an external computing server. And the application in the drone, which was run in a Raspberry Pi embedded in the drone, captured images using a web camera also embedded in the drone, and streamed these images to the server, which replied with a command to move the drone, which was sent from the Raspberry Pi to the drone through serial port. And in onboard computing, we used specific low power consumption boards with specific capabilities for executing inference tasks, and run the complete application in those boards. And in this case, there is no transmission legacy at the expense that computing takes more time. We evaluated offloading in 3 networks: a commercial 5G non-standalone network from Orange, a private 5G standalone network that we deployed in our university, and a Wi-Fi network to compare with other works in the literature. In each of these scenarios, we tested both offloading to cloud platforms, and we used Azure for this, and edge platforms. Regarding the edge evaluations that we conducted in the university with our 5G network and also with the Wi-Fi network, we connected we deployed the edge we implemented an edge platform on our data center, and we connected where the core network of the 5G network is also deployed, and we connected to this data center the Wi-Fi AP. So all these elements, the core network of our network and our Wi-Fi network and the edge platform, are collocated. As for the commercial network, Orange gave us access to the edge platform, which was managed by an external provider. And this meant that the edge platform was not collocated with the core network of Orange, but theoretically there is a good link between these two entities. The more relevant difference between the network setup is that whereas in our private 5G network, the core network, the base station, and the base station, everything is collocated. In the case of the commercial network, the base station is here. You can see it here, close to the university. It's a big red mast. But the traffic is sent to the core network, which is not here, it's in Madrid. So the traffic is transmitted to the base station, then to Madrid, and then to the cloud or the edge platforms. And therefore, the data path is longer, and this will impact on the network delay. This is the architecture of the end device, the drone. In offloading setups, it was embedded with a Raspberry Pi and with a web camera to capture the image to be streamed. And in the evaluations, we used a 5G network. We also embedded a 5G model. And in onboard computing, the Raspberry was replaced with the appropriate low power consumption board. And for this, we used 3 boards, 2 NVIDIA Jetson boards, the Jetson Nano and the Jetson Xavier NX. And for the third setup, we used a Raspberry Pi with an Intel NCS 2. The evaluation we made consisted in measuring the total service delay, considering as the time elapsed from when we capture the image to when we receive a command from the offloading server to command the drone to move. And we performed this evaluation for all these configurations, comparing cloud computing, edge computing, and onboard computing. The results are summarized here in this table for the 3 contributors to the delay: the transmission of the image, the transmission of the command, and the processing time in the offloading servers or the onboard board. And as shown here, edge computing has reduced the delay on average over 10 milliseconds in the transmission of each image, and in the case of the commercial network, for more than 20 milliseconds in transmission of commands. And comparing the private and commercial network, we see that the private network performs significantly better, with a reduction of around 20 milliseconds in the transmissions. And as I mentioned it before, this is mainly because while in our network all the elements are collocated, in the private network the traffic is transmitted from Vigo to Madrid. Regarding onboard computing only one of the boards outperforming cloud results, while the other two performing even worse than offline in cloud computing and edge computing. At this point, I have mainly focused on the transmission delays, but it is important to also consider the impact of computing delay on the results. In the end, this delay does not depend in whether you use edge computing or cloud computing, but it depends on the characteristics of the computing equipment that you are allocated by the platform. And this column here shows, well, the total delay, but also compares with a value that I estimate, well, computed by assuming the setup that delivered the lowest transmission delay in a 5G network, which was our private, when using our private network with edge computing. But instead of using the computing delay or delivered by this setup, we used the delay of the setup that showed the lowest computing delay. And as shown here, in our setup, the private network with edge computing, we could even reduce by 30% the delays if our edge platform performed as better as the edge platform from Orange, which is, I think, a significant difference. On the other hand, we have defined some criteria to set which solutions are suitable for our application based on the mobility of the users. To sum up, the criteria basically considers a solution feasible. It is able to provide service delays that can yield commands before the user can move 1/3 of the frame. And in this case, in onboard computing, two boards could not meet the requirements when the user is running, and none of the boards can do it when the user is cycling. And in offloading, all the solutions can track a person running, but only solutions using edge computing can track a person cycling. Of course, this is adapted to our use case, and results will depend on the computing requirements of the use case in analyzing. As less complex applications would reduce significantly the service delay in onboard computing, whereas no significant impact may be perceived when uploading, whereas more advanced computing use cases would impact even more on onboard computing and may receive comparable, when we compare onboard computing with offloading, we may see much better performance in offloading. With this evaluation, we have concluded that edge computing can effectively reduce delays. We have measured that delays can be reduced by up to 10 to 20 milliseconds in 5G networks. And moreover, we have highlighted the importance of the computing capabilities on the offloading server. Summing up, in this work, we implemented an artificial intelligence applications to evaluate edge computing, cloud computing, and onboard computing in different scenarios, and assessed the performance of service in terms of delay. We thoroughly analyzed the results and provided more detailed insights in the thesis. Finally, My last contributions target one of the primary challenges of edge computing, which is the allocation of computing resources to end users. This is a complex task. As discussed in the previous chapter, performance may be affected by the distance between end user and the server where the application is run, but mobile users may hand over to different base stations while consuming the application, so the path between the user and the server may vary during operation. We also have highlighted the impact of the computing delay in the overall delay, which may vary not only in the capabilities of the server that is allocated to the user, but also on the load in the server. Therefore, the Edge platform must implement solutions to allocate computing resources to users according to their location, but also to the load of the servers. In this work, we propose a simple and lightweight solution to address this problem. The most distinct aspect of this solution is that it delegates the selection of the Edge server to the end device, as opposed to using an orchestrator in the Edge platform. To do this, the Edge platform must implement a network architecture supporting NDN, network name data networking, so that services deployed at the edge are published using names instead of using IP addresses. The idea is to create a hierarchy of edge servers grouped by location, and to access a server in a specific area, the end device must use a query like this one, including the name of the service and the ID of the server, which includes the areas, the hierarchical areas where the server is located. The end device will use wildcards in these fields, those related to the server and the hierarchical areas, if it does not know to which server it should contact. For example, during the first request. And in this case, the request is broadcasted to all edge servers in the selected area, if any. The end device will keep the ID of the corresponding server from which it received the first response, the fastest response, and subsequent request will target this specific node, as it will be considered as the optimal node, at least at that time. Then the device will monitor the compliance with the service delay by monitoring the delay of each subsequent request, and if any requests that do not meet the target requirements, it will contact with nearby service by using wildcards in the NDN query. And to validate this solution, we implemented this framework in our 5G network. We deployed a test service in 2 servers, and we simulated the 2 base stations between them by adding artificial delay to the network interfaces of the servers towards the core network, and simulated handovers by switching the artificial delays on these interfaces from one interface to the other. The end device, the application in the end device was implemented following the procedure I described before. We measure the delay of the service while using the solution, triggering a handover, a simulated handover, every 2.5 seconds. And this is the result. Using the solution, the on-device is able to fix problems related to excessive delay in edge computing. as soon as the request the service delay is greater than the threshold, the next request will be broadcasted to closer servers, and the new optimal server will reply faster, and then the UE will consider this new server as the optimal one, and will send subsequent requests to this server, and therefore the delay is automatically reduced. In our evaluations, we implemented the solution in such a way that the device waits for the response of the service, even if it's delayed more than the threshold, as shown here in this image. But another strategy would be to set a timer on the threshold and then send the new request as soon as the threshold is overpassed. As soon as the threshold, the timer expires. And this way the reaction is better. In summating this work, we have proposed a new framework that delegates to the UE the responsibility of selecting the most appropriate edge computing server and ensuring compliance with network requirements. The solution proposed in this work does not require any complex orchestrator at the edge platform, nor sharing private information such as the location of the users in real time from the operator to the edge platform. And instead, it conceals the responsibility of ensuring service compliance with service level agreements to the end device itself. By selecting the edge server based on the response time, the solution not only considers the edge server that has the shortest, the lower transmission delays, but also the aggregate, but instead the aggregate service delay considering the computing delay, the processing delay, which depends on the current loads on the server. We have just described a baseline framework on top of which different implementations can be developed to improve some limitations. For example, an NDN router could be implemented between the end device and the servers, the edge servers, to filter, for example, the number of servers to which requests are broadcasted. Or also we could implement a ping service that does not impact significantly on the computing loads of the servers, but can measure the transmission delay between the user and its server. And we have validated the solution by implementing a real-world test. Well, these are all the contributions we have made in this thesis. And with this, we have fulfilled our original goals. Contributions 4 and 5 have characterized machine-to-machine and edge computing use cases. Contributions 3 and 4 measured the performance of a specific use case in 5G networks. 1 and 4 deal with the reconfiguration of RAM resources to improve performance, and the same has been done for core network in contributions 4 and 6. And I would like to remark that most of this work is not only theoretical, but we have developed real-world implementations to validate our proposals and also measured their performance, as well as validated the feasibility of these solutions. The results of this thesis have been published in 5 publications, including 3 journals, 2 international conferences. Moreover, we are working on an article based on one of the contributions, and in addition, another article and a conference paper about 2 works that have been conducted as part of this PhD, but unfortunately I could not include them in my thesis. But in total, 8 publications will result from this PhD. But in addition, during this period, I have contributed to another 6 journal papers and 1 international conference in topics closely related to my work. Moreover, I have conducted a research stay at Ericsson in Sweden, where I worked on several aspects related to network slicing. And well, I've proposed a solution around this topic and built a testbed to validate it. And during this thesis, I have been working on several national and international projects, working together with companies such as Orange, Telefónica, Cellnex, and Stellantis. And this cooperation has led to discover insights and get ideas that led to some of these contributions I presented today. And finally, during this thesis, I also developed a testbed that helps to visualize easily how edge computing can improve performance. This system was awarded the second prize at the Meg Hackathon, the ETSI Meg Hackathon in London in 2019, with the second award. And today, one version of this system is displayed at the Vodafone headquarters in United Kingdom. This is the end of my presentation. Thank you all for your attention. And I would like to thank, just 30 seconds, the people who have supported me during this process, especially to my parents, my supervisors, who gave me the opportunity to work in these cool things, and my friends and colleagues that are here or not. But well, thank you all for your support. And now I am at the disposal of the tribunal for any question or clarifications.
Right, okay. Okay, David, thank you very much. That was a very clear presentation and very well structured.
Thank you.
Yeah, so just a few remarks, my preliminary analysis. I felt that the piece was quite well written and quite easy to follow. Also, I felt that the research challenges are very relevant as well to beyond 5G or 6G systems, so it might have the possibility to have some kind of commercial exploitation afterwards. And the thesis itself, I think the links to the research chapters was quite well. I think very well linked. There is a nice copy. It was quite nice addressing the common scenario. Right challenges, which is kind of in the, you see the interdependencies that could impact the overall system performance in terms of computing and communication. Also, I felt throughout the thesis there was a good balance between analytical work and practical experimentation. So the two kind of were coherent and they supported each other quite well. So they were my preliminary analysis. So what I'm going to do now is question to my colleagues here. That will carry on the discussion. So who would like to go first?
Okay.
Yeah. Go ahead.
Hello, Danny. So first, I would like to thank Vivian and Javier for inviting me today here. It's a pleasure. I've never been big. So I will first give you my overall assessment of your work, and then I will make you a few questions. I begin with the objectives of the thesis. To be honest, I have to admit that when I first started reading the document, I said, wow, so many topics, 6 different topics.
It's doing quite well.
You must be either brave, unconscious, or crazy, which is not the case.
I don't know.
So, congratulations.
Thank
Javier and Felipe will have to explain how we managed to convince you to cover so many topics before defending the thesis. So I also acknowledge that the topics are relevant and timely. So I guess that your supervisors have something to say in that. So congratulations to them. Then I move to the research methodology. As Jonathan has said, you have combined analytical models, simulations, and test beds. Many test beds. And this is what I really recognize the most, the test beds. Because when you simulate something, everything is predictable. When something doesn't work, you can dig deep to see what is not working. There are a lot of assumptions in simulations. A different story is commercial networks. That you can hardly see anything, you can hardly touch anything, you can hardly measure anything, but at least you have lots of documents. Everything is well documented in commercial networks. But this is not the case in test beds. Everything is open, nobody helps you when something doesn't work. You have to take lots of hours trying to find bugs in the codes. Every time there is an update of the software or the hardware, then everything fails to work. And then you are always crossing your finger that somebody has already done what you are doing to solve your problems. This is I have to acknowledge that. It's really hard to find someone that spends so many hours in test beds. Young researchers don't want to work in test beds. That's my experience. They want to do AI, commercial networks, and test bed is something very ugly for them. So I really acknowledge the effort that you have spent in that. Also, you have shared code. So thanks for sharing science also. And regarding the novelty and quality of your findings, it is out of doubt. You have 3 articles in DCR. You have 2 international conferences, and the document is like it's brief, concrete, and it's carefully written. So congratulations. And for all those reasons, I think that your work is excellent. Having said that, I have to make you some questions. And I will start. The first one is easy to answer. You have mentioned that you have been in Ericsson, Sweden, in Spain. Can you explain what you have done there and how it is related to the PhD?
Okay, the thing is, I cannot tell all because I've seen it on DNA, I don't remember. So yeah, I cannot explain in which specific topic I work. I just can say that I worked on network slicing. I have done.
If you feel more comfortable, I have signed DNA agreement with Ericsson.
I'm not just
The thing is that we worked on a specific relevant topic of network slicing. There is a current issue that has not been solved in standards, and we defined a solution. We built a test bed, and the thing is that one of the papers is pending to be published. Well, I need to end writing it because it needs a lot more of work before it is sent for publication. But we have defined a solution for resolving this issue. Defined a test bed in which the solution apparently works, and we will make a publication about that. But I cannot, explain which is the current issue that we want to solve until the paper is published at least. I don't know if I can provide more
You have
details.
said that it's related to test beds.
It's related to network
Because
slicing.
I'm not interested on the core
Hmm.
of the thing you did in Ericsson, but just how it is linked to the PhD.
Maps to your contributions.
Yeah, that's it. It's related to
No, it's
radio resource management, radio. It's related to the core network. Is it related?
it's kind of related to radio, I guess, kind of. But lies between radio and the thing is that is an additional topic, like
Seventh one.
yeah, a separate one. It's a separate one, but it's somehow related to reconfiguration of nodes to achieve better performance. But and yeah, it's related to network slicing, how to achieve better performance in 5G networks. Yeah, but I can. The thing is that if I say more, I say exactly which is the problem.
Okay, so second question. You mentioned that the SDR that you have tested was not optimized for fast configuration.
Yeah.
And I wonder, are there such models?
I don't think so.
Yeah.
But I mean, if you need an SDR based on an FPGA that allows you to do these configurations, I mean, I guess that you can implement one SDR that allows to be reconfigured quicker, at least if they have, like, for example, two. In fact, maybe we can use one of these SDRs for that, as they have like two channels and move from one channel to another. Like, I don't know, it might exist some work pending to be done in SDRs that have like two independent channels, let's say, and maybe we can pre-configure one when the other is still under operation and then do the migration quicker. But the thing is, what I was thinking about when I say that is that maybe a manufacturer can implement an FPGA with a specific hardware that can perform these reconfigurations quicker. But I don't think that the manufacturers of this FPGA, which is the Tesis P210, consider this. In fact, I don't guess they consider that a person will be switching from configurations in real time. But yeah, I mean that.
Okay. And another question is, how do you think that all the conclusions are applicable to other USRP models? The M300 series or
Yeah.
SDR?
In fact, I already tested with another SDR, not from Etus and LimeWire SDR, which is very much more cheaper. It's completely applicable. I guess that the thing is that all USPs for configuring the USP, you need to do the same steps. It may take longer or shorter. And if there are more steps, they are steps that are like additional steps for that specific USP. For example, this USP needs to be loaded with a firmware, but you can do it beforehand, and then you do need to do it unless you unplug it, the USP. So all additional steps that are not related to the configuration of the sampling rate, central frequency, bandwidth, or whatever, radio parameter that could be required by the upcoming radio service, they can be performed beforehand. And yeah, I think this work could be applicable to any USP, to any SDR, sorry.
Then we move to the coexistence of Wi-Fi and license assisted. You mentioned that the analysis of network capacity is focused on the downlink, where the data transmission are initiated at the station. And I don't see the point on the number of end devices in the uplink. Do you think that all the conclusion would be the same for the uplink? I didn't understand that.
Okay.
paragraph that you try to explain the difference between the downlink and the uplink.
Yeah. The thing is that I don't remember exactly what was the issue right now, but it's related to that if transmissions in the downlink, the transmissions are in Wi-Fi are allocated by the access point. I don't remember right now. There is there was actually a reason for that.
It's just a matter of the scheduler. It takes more time
mm,
to apply for resources or that paragraph to me, I couldn't understand what you were trying to highlight.
To be honest, I don't remember
But
right now.
anyway,
There was a reason for that. But I don't remember.
okay, don't worry. Let's start to the next one. So then in the coexistence of Wi-Fi and LTE, you also assume peak throughputs. Actually, in your test bed, you put your UE really close to the access point. I think that's 1 meter. And I wonder whether the result would be the same if you have a cell edge user that is affected by propagation or interference.
If I have a, sorry.
If instead of locating the mobile really close to the access point, you take it to the cell edge, where you get interference from other cells, then is LTE more robust than
Yeah.
Wi-Fi? It's just a matter of scanning things, or
Yes. The thing is that this is just a baseline study that considers analyzes how the performance the performance of the devices when the resources are distributed among the technologies. The thing is that, well, there are different specific scenarios that we could test. For example, one depends on that, but I think that in this specific scenario, it's just you just need to adapt the results of the Wi-Fi or LTE devices to the modulation being used, also to estimate how many frames are discarded or, well, could not be demodulated by the devices. I think that's an additional work, let's say. But you can, I guess, in that specific scenario you have described, you can just add this information, like estimate the throughput in terms of the signal, the quality of the signal of the devices. Another thing, the thing that I commented in the thesis is related to, for example, the hidden node problem, or specifically what I commented is when two devices are from different technologies, are two apart from the other, for example, because in this specific case, which is, as I said, reported in the literature as a relevant issue, the thing is that devices can, well, to transmit, they measure if there is any pending, well, any outgoing transmission being performed, and they do that in two ways. First, they analyze the power of the channel, and another thing is that, well, they are able to decode signals from their own technology below that threshold. So if there is a device that is far, but and the transmission, the power at the reception is below the threshold, but it's still below the minimum that the Wi-Fi device, for example, is able to decode, Wi-Fi device, even if this frame is not the target of this frame, they will understand that there is a pending frame, Wi-Fi frame. They will get which is the duration in the field of the transmission, and will defer from transmitting during that period. This also occurs with LTE. What happens when the transmissions are from different technologies? The devices will check the medium, the power will be below the threshold, but they are unable to detect there is a Wi-Fi transmission if there is an LTE transmission device, or vice versa. And therefore, they will transmit and a collision may occur. And in this case, as I explained, as our proposals multiplex the transmissions in the time and frequency domain, the results will not be affected, but the actual results of direct resistance are lower, and therefore the difference between our solutions compared with direct resistance are actually greater than what we shown in the table.
Next question would be related to the computation of loading. You have shown that when you use the the commercial Mac, there were strange peaks of delay. And why is that? At which hours did you perform the experiment? Was it by night, or was it in the middle of
it was at night. I scheduled the test to be executed at night, like, I don't remember, by something like 4 a.m. or something like that, in order not to collision with
maintenance issues.
I don't know, because we don't have any more access to the Edge platform, but yeah, it's weird. It's weird because it does not. In fact, it does not happen with we didn't see this effect in cloud computing, which were performed at the same time. I mean, both the cloud computing and edge computing evaluations were performed in the same conditions. And as you can see, we had peaks of delay that were higher in edge computing than in cloud computing, which has no sense. But yeah, the only reason is that the link between the operator and the edge platform is faulty. That is out of our control. We just put the results as we experience.
Another question is related to the measurement of delay. You mentioned that you are using network slicing both in the radio network and both on the core.
Yes, we have a radio in our laboratory and also outside from CITA-T that is connected to a core network from Open 5 years. We configured the network slicing in both the core network and the radio. We wanted to test how the delay on the network slices is according to different values or throughput in the different network slices. We created a high priority network slice and a low priority network slice, and we wanted to test if we try to saturate the network with low priority slice, does it affect to the high priority slice? Because this should not affect to the high priority slice. With this, we effectively show that no, the latency is still low, even if the high priority slice is the low priority slice is congested.
For the radio, you were using open air interface?
No, the CITA-T. Okay. We have a carrier grade base station from CITA-T that Telefonica has implemented for one project we have with them.
So then, next question is related to the drone application, the computation upload. You have shown some delay values, and it was that table on the right. I guess that those are the delay budgets
yeah.
for different applications.
For our application,
yeah.
For our, well, we just set a criteria because the revisors of the corresponding journal instead has to set a criteria to show whether the application is
And then you divide that target in different components. And you take the image transmission delay and you assume that you already have the image. So I didn't see any delay related to the capturing device. If you use CMOS or CCD sensor, then it takes a whole frame to integrate the light that is coming to the camera. And then you have compression. You have compression in your test bed, in the webcam.
Yeah, but the thing that's out of the scope of the evaluation.
But it is in the delay budget.
No, because we measure the delay
based on the distance that the guy is traveling out of the image.
No, but I mean, these results, those related to image transmission and the overall delay, are from the image, from the timestamp at which the image is sent, not captured. As you said, and I didn't realize, in this case, there is the delay is higher, the service delay is higher because there is a delay from
fixed bias of the
yeah.
Probably this is the whole delay that you can have. You have to subtract the capturing delay and then
the capturing delay is not here. I didn't realize about that.
And that was my last question. I don't want to take all the time. Thank you.
Thank you very much.
Okay, first of all, I want to congratulate you. I'm not going to say many more things because I think but I really want again to remark even that yourself have done it. You have this test bed is something great. I mean, simulation is good, gives you some insights of how things works, but you can say, I mean, some thesis said it works. Yours said this works. Okay, so this is something that I really want to highlight. Okay, so great job, and of course, I have some questions, and I hope that I can understand better. I mean, I think these questions are a little bit outside of the thesis because the thesis is really understandable. So those things maybe some apart, but I guess maybe you can give some information to us. So in the third chapter, you can say, I mean, there's several tenants sharing some infrastructure. I mean, this is what you have. You have these two. I mean, my question is, what happens when there's a peak demand? How you can guarantee the SLA of the tenants somehow? Do you study this? It's completely out of your work.
But peak demands on what and which regard? From users?
Yeah, from users maybe. What happens in that case? I mean, you have an infrastructure that you can share, but how can you help tenants to fulfill their contracts?
You mean, for example, if a user here starts to, for example, do a speed test or whatever that requires a lot of resources, and you consider that you need to allocate.
But the thing is, you have to allocate him with some resources, but there's another user from another tenant that is demanding also a lot of resources. What happens there? Do you have something?
I think we did not consider that. I think that's the enabler for the. I think the technology, let's say, we propose is the enabler for allowing operators to be relocated to different radios. But as you said, it is relevant that if we take the effort to relocate an operator just to attend a user, which by the time we relocate the operator has ended operation, the strategy that the infrastructure provider has to implement to determine how radios are allocated to two operators need to consider that obviously. Maybe, yeah, I don't know. That's something that has to be considered, but to be honest, it's out of the.
I know it's out, okay,
Yeah,
because as I told
but-
you,
yeah,
it's
but
big,
it's-
that
Yeah,
I was wondering.
it is relevant, but the thing is that, for example, maybe this could be triggered by a communication between the operator and the infrastructure provider, and the operator may be able to tell if the user is going to have a longer connection if they know which services are being consumed by the user. For example, if the operator knows that this specific traffic that is being consumed by the user is a speed test, they may just skip it. But if it's going to use Netflix, then it may be more interested in allocating the base station. It may depend also in the services being consumed by the user, and yeah, maybe may consider, well, the operators, as far as I know, may have a track of the location of the users in the past, so maybe they can predict how well, if the user can move from one location to another, how well, if the user can move from one location to other, and if it's probably that the user can move, then the 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 probability of the algorithm to allocate a radio, to request the location of a radio, just to attend that the user will be lower.
Okay, let's move to dynamic time multiplexing approach. I have just a question about bandwidth. I mean, you need some kind of signaling, I guess, to decide which one of the technologies needs to transmit its time. And I wonder if it's, I mean, if this overhead is too much, it's too slow, it's what?
Okay, you mean the overhead of transmitting this CTS, which is the
This is the only signaling you need. I mean, maybe yes. Now
Well,
that I'm thinking, maybe yes.
this is the only signal you need to communicate to the users, but you may need to transmit a signal from an orchestrator to the Wi-Fi access point or the device that transmit this frame in other case. Yeah, we did not consider the other delay, the one related to the orchestrator, because I believe that, for example, it can be kind of scheduled, like the orchestrator may tell that instruct the Wi-Fi access point to transmit the CTS in a specific moment, or even can schedule it in periodic intervals. Just if the period needs to be adapted, then yeah, just send these reconfiguration messages if needed.
And that's good. As today, commercial phones are able to use the CTS cell to
Yes, indeed they do, because this is out of this project, but I have seen that devices, Wi-Fi devices, usually for some reason use this to get better performance, especially iPhones. I don't know why, but iPhones periodically send CTS just in case they have something to transmit. Then for the next 100 milliseconds, the channel is hidden because all the devices are deferred for transmit, and if they need to transmit, they do. And that happens a lot with iPhones, but also, for example, my mobile phone, which is a Samsung, also do it from time to time. But with iPhones, it's crazy.
Okay, and I have a question in chapter 5 about, I mean, you propose a method to evaluate one-way latency.
What?
And I wonder, what are operators measuring right now? Do they have something to get this information? If you know, I mean.
Okay, the thing is that this has arisen because we had a problem with our own network. We have the base station from LTE, we have our own core network, and we have the credentials to enter in the radio and test things and change things and check the logs, create specific logs, and we were unable to measure this. So I guess that the operators do not have any mean to measure the delay in one of the communication. And what I think is that up to this moment there was not need to do that because there were not any applications requiring such specific, such a stringent network, delay constraints. So, yeah, I don't think operators have any means to measure the latency in one path. Maybe there exist base stations that implement it right now, but I don't know. Ours is presently is a 5G base station and does not have any mean to do that.
So let's move to the chapter 6. I wonder, I mean, you mentioned, not in the presentation, I think only that you aggregate several flows instead of using one for each user. And my question is, did you study or analyze or have a criterion to make this aggregation? I mean, could be different if the groups are different?
Yeah, the thing is that, in fact, I don't know if I remember to tell it during the presentation, but the thing is that we consider the worst use case. We allocated distributed the SDN flows during the analysis uniformly. And that means that both malicious and from different traffic classes. And therefore, we have the 4 traffic classes, we have different behaviors, and some of them are very different in terms of throughput. I think that one traffic class, the one which transmitted the most data has 100 times that of the simpler traffic class. I don't remember right now, but there was a significant difference. And we allocated them uniformly, although it is feasible to do it by traffic class, so that SDN flows only contain data flows from the same traffic class. And if we have done that, then these graphics will be like all in the one. And it will be quite strange to send a journal article with just a paper with graphs in which we say that in any case we detect everything. And therefore, we just consider this a worst case in which they are allocated
So of course, an
uniformly.
impact, but you can improve even your results.
Yeah.
Okay, great. And did you compare, I mean, did you measure the accuracy, for instance, in the case you analyzed all the traffic? I mean, we have here the results when you have these 2 slides and you only inspect those packets that goes to the suspicious one. Okay, but did you compare? I know it's not feasible in the sense of computing, but did you compare with analyzing all the flows, all the traffic? Maybe not. I mean,
No, I did not understand the
the
question.
question. Okay.
Sorry.
What I wonder is you have the results when you separate the traffic, okay? And you have the malicious one going by one of the slides.
No. This is analyzing when the traffic is mixed.
But the traffic is.
When the traffic is mixed. And then we separate the traffic.
Yeah, but you only, I mean, when you separate, okay, it's analyzed when it's mixed, and then you separate them, but the inspection of the packet is done inside the malicious slide.
The inspection we do is to move this.
Yeah, but it's a light inspection.
Yeah.
Okay.
What we propose is to move the traffic to that quarantine slice. And
Yeah.
regarding how the traffic is analyzing there,
You don't
that's out of the
know
scope,
it's
and
out of the scope.
we guess that all the malicious traffic is detected somehow. But
Okay, okay, so my question is, has no sense. Okay. And you mentioned you have two possibilities also, having this quarantine slide also up. And what I want to know, if you were an operator, which one of the solutions would you take? Reactive or proactive?
I think it would depend on how often you detect you are running this inspection, because if you just have to analyze data flows with this um, legacy inspection tool, not that often, I don't know, maybe one each hour or whatever, then you may remove the network slice and deploy it when you need it. But if you are constantly analyzing the traffic and there is constantly traffic to be that deviates from the expected behavior, I guess that the most optimal solution would be to keep the quarantine slice up all the time. It would depend at which, on the frequency at which traffic deviates from the expected behavior. That's not.
I think I have a last question about broadcast messages in the last case. And then again, this in the wrong one. Not in the wrong, no, I think.
No, okay. Broadcasting here, yeah.
Yes. Again, which is the cost of this broadcast? I mean, it takes a lot of bandwidth.
Yeah, I understand.
Because you mentioned it's small, but what is small?
No, I don't think it's that
small.
small.
Is something undefined. Okay.
No, it's not small at all, in my opinion. What we believe is that first, it takes an impact, because if we are broadcasting actually um, requests that need to be performed in the servers, it's not the same to perform it in one server that in all the servers that the platform has. So therefore, it's a relevant question. The thing is that what we can do is to, as I said, implement um, um, an NVM router here that processes the request from the user, and in that case, in the case we are broadcasting, we just select a few nodes to send that request in order not to compromise the complete infrastructure, because it's not reasonable to send a competing request to any server in the infrastructure. But yes, of course, I think, in fact, it's one of the disadvantages of this solution. But on the other hand, I think that it can also be fixed with many mechanisms. One is this, another would be to implement a ping service that simulates this behavior. But for example, imagine a ping service that the ping is, well, the initial message is broadcasted to any server, for example, or it can even be filtered by an NDN router. But once it reaches to the server quickly replies, so that we only measure the transmission times, but it can also be improved in such a way that somehow the server indicates its capacities and load, the current capacities and load, and somehow the UE or an intermediate node can estimate which is the processing time on that server. But as I said, there are many. This is just a baseline model or framework that can be complemented in so many ways to overcome possible weaknesses.
Okay, just to finish on the question that I on the same
That's fine.
level. Me voy a cambiar un momento en español porque como tenemos, no sé el público, si todo el mundo habla inglés o no,
No, todo.
pues entonces simplemente quería volver a reiterar que enhorabuena por el trabajo que has hecho de él porque es muy bueno. Bueno, ya lo han dicho ellos, lo repito un poco, pues eso, experimentación, simulación, teoría, está todo un poco, está todo ahí, publicaciones muy buenas, objetivos cumplidos, entonces, pues enhorabuena de nuevo.
Gracias.
Thank you very much. Okay, David. Okay, so I'm trying to now identify some questions that my colleague can ask. Okay, in chapter 4, so we talk about spectrum management, LTE, Wi-Fi, right? Now focusing on the dynamic spectrum management for the time case. So, what would cause it to deviate from the ideal performance?
Okay. I guess that what you mean is that if you plan to split the time at which one technology and the other transmit, for example, 10 milliseconds one, then the other, what can happen is that you, when allow the Wi-Fi transmissions, well, the thing is that you are not like splitting the okay. How to say? When you are doing this, you are actually blocking Wi-Fi devices to transmit to perform LTE transmissions, and on the other hand, as you control where LTE transmissions or 5G transmissions are performed, you don't need anything to that in that regard. However, when you allow Wi-Fi devices to transmit, in the downlink you can just split, like, okay, maybe that's the, sorry.
I told you that we can skip
Yeah.
it and then you will remember.
Yeah, that's the relevant, the thing. I think I can explain it verbally. The thing is that when the transmission is performed in the downlink, you can control when it ends. So if you know you have to end a transmission in 50 milliseconds, you can adapt the transmission to be performed so that even the acknowledgement is received within that period. What happens in the uplink that the transmitters, you cannot instruct the transmitters that they only have this time to transmit, and therefore they can start a transmission and keep transmitting until they end. And when using impedido aggregation, I don't remember the numbers, but they can concatenate several Wi-Fi frames, and therefore transmissions may be extended, like do not end at the moment the system was planned to allocate to reserve the resources for the LTE transmissions. That's what I mean, and therefore the Wi-Fi transmission window would be extended, and therefore the system should to adapt the planification, the scheduling, so that the system should extend also the LTE transmission window in order to balance it. This event.
Because if Wi-Fi transmission is actually hyper, then the system is.
Sorry?
If you have a high load on the Wi-Fi, then the performance is going to degrade because the CTS frame has to. Because you said in the piece it doesn't prioritize ongoing traffic.
It does not prioritize.
Doesn't prioritize ongoing
Ah,
traffic.
yeah.
So you have to.
Okay. Yeah, the thing is that by itself, the CTS uses the same EFS, the time that Wi-Fi devices defer before starting a transmission to check if the channel is even, the same IFS as data. And therefore, if we use this default EFS, then we have to contend with end devices transmitting. That's why I propose to use reduced EFS that maybe match those of the acknowledgements, because we can, as an access point, predict where they can be transmitted. And therefore, that's the reason why this approach, this specific approach, should not be implemented in any regular scenario, because, as I said in my thesis, the CTS does not block the transmissions of the Wi-Fi PSS. It blocks the transmissions of all the Wi-Fi devices in the space. That's relevant.
So yeah, that leads on to my next question, because then you clearly have two alternative approaches, advantages, disadvantages, and that's going to ask. And if you wanted to deploy this solution, when would you, which are the ideal scenario?
You mean why choosing time versus frequency? That's better explained in the thesis, but the thing is that it mostly depends on the bandwidth of the channel in which we operate. For example, this is more easy to explain. In Wi-Fi, the lowest channel bandwidth is 20 megahertz, and therefore, if we divide the channel by 4, in this case, we use the frequency domain approach. We could not use any bandwidth at all because there is no 10 megahertz channel bandwidth. But in other cases, it depends on, for example, in the data rates that can be achieved at different bandwidths. In this regard, in LTE, the peak rates, the data rates, are linearly dependent on the frequency resources that are allocated to the end user. In Wi-Fi, transmissions, well, at least Wi-Fi 5 and other legacy technologies, they use the word bandwidth, and the data rates do not linearly depend on the bandwidth. If I don't remember, I think that 160 and 80 megahertz channel bandwidths have the same data rate per bandwidth, but then in 40 megahertz channels they perform better than in 80, and 20 they perform lower than 40. I think they perform lower than 40 and also than 80 and 160. And therefore, what it happens is that, for example, in this case, it's clear when the Wi-Fi channel operates in 40 megahertz, it performs better than when performing in 80 or 20. And therefore, the frequency approach, which is the one that splits the channel in frequency and creates a channel of 40 megahertz bandwidth, performs better. In these other cases, let's say that when using the frequency domain approach, the channel is performs better per megahertz than in other channel bandwidths, and what we have is, on the other hand, that the time domain approach has a little downtime because of the TTS.
Yeah, I get your point.
Okay.
Yeah, I get your point. I just wanted to probably emphasize, maybe, to make the advantages, disadvantages more clear, maybe to use a special efficiency.
Yeah.
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 To show better
Yeah, to be honest, it's true.
chapter 6, so the lightweight mechanism for detecting IoT traffic patterns. Right, so in this approach, so you're detecting, effectively what you're doing, you're detecting the statistics of the traffic, of the malicious traffic.
So could you?
Effectively, you're detecting the statistics of the malicious traffic.
Yeah. The
As
thing
part
is,
of your detection capability.
yeah.
Trying to see, I guess, trying to see how it deviates from
Yes, we
the.
collect, for example, each 10 milliseconds, the amount of traffic
Yeah.
being sent or received in each of the SDN flows, and then we just compare with the estimated one to trigger the.
Because so the performance, it depends. I mean, when you identify the new result, it actually depends on quite a few parameters. So the threshold of the detection, really, which depends on the type of traffic.
Yeah.
Transmission periods, threshold ratio. I mean, there's a lot of parameters there. Which one of these you think affects the performance more?
Well, the threshold, obviously, because if you put it at 1, then you will almost send everything to the quarantine slice, and obviously you will detect all the malicious traffic as long as they deviate 1 bit from the expected value. Whereas on the other hand, if you put it if you put a higher threshold, then you will not detect anything. Other parameters that were, well, the thing is that that's the only one you use to detect. In this analysis, in this analytical model, we considered how, well, we used other parameters, but for detecting, that's the only one used. We compare the estimated throughput when the throughput we actually measure. Yeah, but for the technique, we only compare the throughputs.
Because I think something that also affects the performance was the reassignment of the context flow. The reassignment of the context flow.
The reassign?
Yeah, you miss when you quarantine slice.
No, that does not depend on the detection.
No.
The thing is,
the general performance.
the general performance. The thing is that that only depends on how quickly you react. But for example, if you need to remove this traffic in target time, then the delay is equal to the sampling rate on the SDN system, that is the frequency at which you collect the data, and then this. You have to sum these two things. But it does not affect to how much malicious traffic
Not the detection, but the general performance.
The general performance.
Yeah, because we got the slide.
These two.
Those to the top. The dynamic the dynamic relation of quantities. That's what I was referring to.
You mean what does
570 milliseconds.
So,
570 milliseconds. The dynamic relation.
yeah, that's to deploy the Docker container.
Yeah. The Docker.
But the thing is that this is only related to the reaction time, not the performance in terms. Okay.
Yeah.
Okay. I was thinking about performance in terms of how much devices are sent to the quarantine. Okay. Yeah. No. That. And what was the question?
Because my point was, I think in now in, for example, in redundancy in the network. So that you actually already sent out redundant computing resources to support. So
yeah.
It's quite compatible actually. So maybe
yes. No.
Maybe this. delay
Yeah,
can
yeah.
overcome.
Yeah, I mean, but in the end, we follow the same approach that 5G networks do. I mean, in 5G, you can have redundant nodes, but in the end, you manage the life cycle of these nodes, how we are deployed and removed, and these things. And we are actually do the same. Just this is like the specific. In the end, 5G networks also deploy the VNFs like ordinarily or in a container or a VM, and yeah, they follow the same approach, deploying the let's say VM or container, initialize the function, and then the corresponding task. But
Then a good question on chapter 7, so page 35, slide 35. Okay, yeah, this is interesting. So, right, so this is just the offloading, so the service delay for offloading traffic. So it seems like all these solutions are quite good. They satisfy the
you can track up the
requirements, especially the 5G private SA tool. Okay. For example, now in beyond 5G network, energy efficiency is an important metric as well. So if I have to choose between any of these deployments, and I want to take energy efficiency into account, which one do you think would be most optimal?
energy efficiency
Yeah,
in the device.
Take into account also energy.
Yeah, we did some evaluation in the thesis and in the corresponding journal because we were asked to do so, to compare what we were, well, he asked us to measure the impact on power consumption because of onboard computing boards, because yeah, we we had an assumption that when we use a drone, for example, that has a limited flight time, or yeah, other vehicle that is powered by batteries, then power consumption is a relevant aspect. And what the results of this evaluation that were that in the specific case of a drone, the difference of power consumption was really low because I don't have the results here, but the power consumption of a Raspberry compared to with a modem, compared to, for example, the Raspberry with the Intel NCS dongle, was insignificant. The difference in flight time was compared to when you just use the, the, the Raspberry for offloading, the difference was in the highest difference was just 3% in the drone. With this board, which was the one that performed better. In this case, this is because the drone motors consume a lot. We may have, for example, another vehicle that has a limited battery, and therefore it will have a more high impact on battery life. If we talk about sensors, then the impact could be more significant, but in any case, yeah, I think that the power consumption of just the board required in this case for yeah, getting the images and transmitting them to the floating server was not even half of that of this board that was the most powerful one. So
I mean, for example, I want to just detect walking and running. Yeah. So which means the 5G private SA and the wireless LAN have two good options. There's not much in it. 57 milliseconds, for instance.
Okay.
So I have to choose between one of those, and I look at it from an energy efficiency as well. Which one would I go for?
I would go for the Raspberry Pi with the Intel NFS2 because in this case, well, first it matches the target required latency, and on the other hand, the power consumption of this board with the NTLS is similar to that on here with the Raspberry Pi with a 5G mod. And you do not need to, to get a mobile data subscription for that. So it's,
if I go fully on board, it's today, I think 16 is quite high.
yeah, but if
If
you
I want to
just,
choose, if I might want to choose 86%. Just for walking around.
okay,
I'm just asking you, which one would you go for? Why the standard 5D or the 5D?
yeah, but the thing is that these results are quite, they are not real because they are performed in the same conditions.
Hypothetical question.
Huh?
Hypothetical question.
But
It's 50-50.
what?
You got 50-50 chance.
No, but I didn't
My
understand.
question is, what is more energy efficient, the 5G air interface or wireless?
What's that? But no, yeah. Sorry, I did not understand the question, but yes, the difference in power consumption when the Wi-Fi is activated is not that high.
Okay. Right. How much for time? And I don't want to ask another question. We've got a big cut time. This is a more general question. So you did a lot of work. You got from the project, so I noticed that as well. On a lot of different topics. Now, if you had to, how many innovations? 5, 6?
How many?
Contributions, 5, 6, something like that. Yeah, anyway. If you had to pick the strongest contribution, which one would it be? And why?
I think that maybe, I don't know, because I think that the most interesting one in terms of commerciality, production, let's say, is this one, because of the relevance of edge computing, and that I think this is a cool solution to publish services with names instead of IP address, and yeah, solving a crucial issue with this paradigm, which is the allocation of the computing resources to the users, and because, for example, the second one, which is the one that took me the most time to produce, what I feel is that operators are not putting too much attention in undefensed technology, right now at least. And well, no, I think this is the most important one for me. Because,
I was going to say,
yeah.
Ericsson, no?
Huh?
Ericsson. Because of Ericsson.
This one? No.
No, this one?
No, I didn't have anything related to this in Ericsson.
I thought you said at the beginning that you're...
No, it was closely related to RAM, but nothing to do with this. No. But I mean that implementing some kind of, for example, artificial intelligence to manage how the resources are allocated and these things to improve how the network works. And given the fact that today it's really important to readapt the network to meet the requirements, I feel this is the contribution that is more important from those that I presented.
Thanks. And okay, last but not least, if I was to pick one of these topics, I wanted to prepare a project proposal, a new PhD roadmap. Which one of these do you think is still a significant challenge to address?
The least significant.
In which one of these there's more significant challenge to address?
To continue the work or to...
Yeah, like a future work.
I'm getting funds.
Maybe
It's more away.
maybe or this one or the one with NDR. Maybe the first one. Maybe the first one once you have this architecture, it will be interesting to create a kind of AI to decide how this is orchestrated and resolve problems like the one Christina highlighted.
Okay, I agree. Yeah, I mean, AI machine learning is a hot topic at the moment. I feel there's quite a lot of the solutions that you presented today with a bit of a machine learning, we will perhaps provide a better or alternative solution.
Sorry. Sorry, I am.
I'm just saying that if you apply machine learning to a lot of these solutions, I think there's still scope there for some interesting results.
Yes. Maybe in this one and
Especially in chapter 6 as well.
chapter 6 as well.
For detecting malicious traffic.
And even in chapter 2, in this one, you could use kind of artificial intelligence to decide how and when and how to distribute the resources. Yeah, I think all of these contributions, well, maybe not this, but yeah, this I don't know.
Okay.
Well, 1, 2, and 6 can be extended with artificial intelligence too.
I think we're good. Okay. Thank you very much.
Thank you very much.
Okay, so I think that concludes the questions. Now I think we'll have a bit of time between us and jury just to discuss the work. Sorry, yes, of course.
El resto, por favor, ya podéis avanzar.